My name is Koen Bertels. I'm Belgian by nationality, but I work in the Netherlands, and now I switched actually to University of Porto in Portugal, where I'm part-time professor, and I'm a visiting professor in Leuven, the University of Leuven. I'm already for 10 years working on quantum computing, which is building a quantum computer. The challenges are extremely big. That's why I decided to start QBee, which is very research and application oriented, so that we can help universities, but certainly also companies, to make the move to quantum computing.
Quantum computers promise to solve exciting problems practically impossible to solve using classical computers.
Quantum research is being taken up by not only the governments but also startups as well as individuals in the university, because everybody has something to gain from this once we can improve the computing power of human society in general.
Classical computers, talking about laptops up to supercomputers, they're made of transistors, and we are at 2 nanometers of the size of a transistor. So that basically means we cannot make it any smaller anymore, but we do need more compute power.
And quantum computers promise to do so, but still we have to be ready in terms that we need to develop the reasoning and common logic in making quantum algorithms for the application.
Right now we are already having small quantum processors. If you are trying to design an application on a quantum computer, we cannot run a full-fledged application on the current quantum processors that are available today.
Quantum computers are programmed using quantum programming languages. These high-level human-readable programs are translated to low-level machine-readable instructions by using a quantum compiler. I am leading the software development effort to implement various compiler features and optimization passes. This enables my team to execute their quantum applications on a quantum hardware or a simulator backend.
Important aspect of quantum computing is you can already simulate quantum computation on a classical quantum computing simulator.
So what we're doing is that I have these PhD students from China, India, Tunisia, Iran. We brainstorm a lot on all these aspects, and we start making small-scale kind of infrastructure for a quantum accelerator.
We do not aim for running the algorithm or the application on the available quantum processors, but try to run them on the small quantum computing simulators and get a taste of the power of quantum computation.
And I think quantum is, in the 20 years that I've been working in Delft, is one of the few technologies that I really see like this has an incredible future of building even more powerful machines.
We have a very high interdisciplinary team here at QBee, from computer science, physics, biology, mathematics, as well as engineering. And all these people need to collaborate together, draw it on the whiteboard, sit together, have coffee, discuss things, and then we can figure out what is exactly required to build the full-fledged quantum accelerated application.
Quantum computers promise to solve complex computational issues in chemistry, allowing us to more accurately simulate and understand better molecular changes and ongoing chemical reactions. We will be able to design materials with the desired properties much faster, but at the current stage, we still need to build the logic behind quantum computational chemistry. And this is what my team does at the QBee.
One of the major verticals that we have is genomics, where we are building a worldwide team of experts to look at these specific kernels that are going to have a very high societal impact in the fields of medicine and in virology and synthetic life, synthetic biology, as well as agnostic biosignature detection.
Chemistry also is related to the applications in medicine, pharmacology, genetics. So it is a thing of future, let's say, and we have to be ready for it. So in a way that classical computers have changed the world 50 years ago, this is the next type of change, let's say, that will for sure come.
Everybody in the world is doing quantum computing, and they call it NISQ, Noisy Intermediate Scale. What is more important is that universities and companies, we have to reason more in terms of perfect qubits. And so that is why we put the label PISC, yeah? So perfect qubits, intermediate scale quantum. Yeah, that looks more at the application side and abstracts away from all of the problems that we still see at the physical level, the quantum physical level.
Quantum computing, I think, is still 10 to 15 years away from making the breakthrough applications that is going to have a very high impact on industrial, societal, and scientific field. But we need to start already now, because it not only requires a lot of training for the people who are designing these algorithms, but also a lot of engineering efforts that are happening all over the world at a very high pace. So only if we start now, we are going to reap the benefits 10-15 years from now.
The QBee mission is that we want to have, let's say, both the industrial as well as the university kind of objective to help universities make the move already to quantum logic in all sciences, and that we help companies to actually start defining what quantum logic implies for the product that they're developing and putting on the market.